Before industrial whaling, the baleen whales of the Southern Ocean ate about 430 million tons of krill a year. More than twice the entire global fishing catch today. Per NOAA Fisheries, an Antarctic blue whale reaches 110 feet and 330,000 pounds, about 165 tons. North Atlantic and North Pacific animals run smaller, around 90 feet, past 50 tons. Its tongue, people say, weighs about as much as a grown elephant. Its heart is the size of a small car. It feeds along the edge of the deep ocean, dropping into the mesopelagic zone where the light has nearly given out, then climbing back to the surface to breathe. We have measured this creature wrong, in the most literal sense. The blue whale model hanging in the American Museum of Natural History in New York, unveiled in 1969, was sculpted largely from photographs of a dead female that washed ashore in South America in 1925, when almost nobody knew what a living one looked like. Millions have stood under that belly in the hush of the hull, believing it was the truth. If one of the great museums on Earth needed 30 years to get the shape right, we are almost certainly still wrong about the harder thing, what it is for. This is the heaviest animal known to have ever existed, tracked by satellite, listened for with hydrophones, counted from survey aircraft for the better part of a century. And the most fundamental event in its life, we have witnessed twice. Measured pregnancy rates run between 33 and 50% a year, meaning thousands of calves arrive every season. The rate at which surveys observe a mother with a calf is 3.1%. Those two numbers cannot both be true, unless we are looking in the wrong place or at the wrong time. Where they go is barely better understood. The calving grounds for most of the world's blue whales have never been located. One thin exception, a female identified by DNA and photographs named Isabella, tracked from the Gulf of Corcovado in Chile to the waters around the Galapagos, more than 3,100 miles away, now thought to possibly be a breeding ground. The answer arrived in February 2025. Trevor Branch at the University of Washington showed that blue whales give birth in autumn and winter, just after leaving the summer feeding grounds, and wean their calves about 7 months later, right as they return. Surveys, meanwhile, run mostly in summer, in the feeding grounds. It happens thousands of times a year, on schedule, just outside our frame. A newborn is already about 23 feet long and weighs somewhere between 6,000 and 8,000 pounds. We have missed the birth of the largest animal on the planet. In 2023, paleontologists described a fossil whale from Peru about 39 million years old and named it Perucetus colossus. From 13 vertebrae, 4 ribs, and 1 unusually dense pelvis, they put its mass between 180 and 340 tons. If that held, the blue whale was finished as the heaviest animal that ever lived. The estimate rested on the bones. Perucetus had pachyosteosclerosis, bone abnormally thick and dense, the kind shallow water animals carry for ballast. In 2024, a rebuttal study led by Gutara reworked the method. At a length of about 56 feet, the real mass came to roughly 60 to 70 tons. Even assuming a generous 66 feet, only 98 to 114 tons. Not a contender after all. The original figure gave Parusetus an absurd body density because it was far shorter than a blue whale, 56 feet against 100 feet, while carrying the same mass. The volume was not there. The same year brought a second challenger, Ichthyotitan severnensis, a colossal ichthyosaur from the end of the Triassic, about 202 million years old, found in England, estimated at up to 82 feet. But the fossil is a single piece of jawbone, so the team published no mass estimate at all, and said even the length remains contested. A title formally challenged twice in 2 years and held both times, not because nobody dared, but because each challenge forced the measuring method to get stricter. Mass. Only mass. Nobody contests the thing the next chapter is about, because on that axis there is no fossil rival at all. No skeleton on Earth can tell you how many tons of nutrients an extinct species moved in a year. Records can be taken. Function is harder to take, and function starts here. In November 2021, Nature published a study led by Matthew Savoca at Stanford's Hopkins Marine Station. From biologging tags placed on 321 baleen whales across 7 species, the team found that a mature blue whale eats roughly 16 tons of krill a day in the feeding season, about 3 times what science had assumed. It came mostly from examining the stomachs of dead animals and running metabolic models outward from there. The 2021 work measured living ones directly, tags logging every lunge, drones sizing the bodies from above, acoustic instruments reading the density of the swarm the whale was driving into. Blue and humpback whales off California came out 2 to 3 times higher too. The error was systematic. Before industrial whaling, the baleen whales of the Southern Ocean were consuming about 430 million tons of Antarctic krill a year. That figure is roughly double the entire remaining biomass of Antarctic krill today. It is more than twice everything our species pulls out of every ocean on the planet in a year, from every fishing fleet combined. One group of animals moving more material than global fishing. And nearly all of it goes in through a narrow window. The feeding season runs only a few months, and most of the year's energy budget is loaded in during that stretch. The rest of the year, the animal lives largely off stored fat while it migrates and breeds. You can hear a single mouthful end, close to a ton of seawater forced back out through a sieve of baleen, hundreds of times a day. Before whaling, there were far more krill-eating whales than there are now. And there were also far more krill. Phytoplankton, the drifting, photosynthetic plants of the sea, live only in the euphotic zone, the top layer where enough sunlight still reaches to run photosynthesis. But nutrients in the ocean are always falling. Carcasses, waste, fragments of organic matter. Gravity takes all of it down into the dark, where there is no light to put it to use. The layer with the light is short on nutrients. The layer with the nutrients is short on light. An ocean governed only by gravity slowly drains its own surface. Here is what interrupts that. Whales feed at depth and then, being air-breathing mammals, must return to the surface, and they release waste at the surface. They are continuously carrying material from below to above. Joe Roman and James McCarthy named the mechanism in PLOS One in October 2010, the whale pump. A pump that runs against gravity, driven by nothing but the need to breathe. In the Gulf of Maine, Roman and McCarthy calculated that whales and seals return roughly 2.3 times 10 to the power of 4 tons, about 23,000 tons of nitrogen to the sunlit layer of that gulf every year. More nitrogen than all the rivers emptying into it combined. When we think about what feeds a stretch of coastal sea, we think of rivers carrying sediment and nutrients off the land. In the Gulf of Maine, the measurement says a group of mammals does more of that work than the river system. The most valuable thing it lifts is not nitrogen. In some seas, nitrogen is abundant. What is missing is a different element, one that only has to be present in a few parts per billion to change everything above it. When commercial whaling in the Southern Ocean ended, scientists expected krill to surge. Take the pressure off, the prey rebounds. The opposite happened. In the Southwest Atlantic, the sector with the longest survey record, net surveys point to a steep decline since the 1970s, the figure most often cited being around 80%, from Atkinson and colleagues in 2004. Our intuition fails because we run a one-way model, predator down, prey up, which works only when the prey has its own food supply. The Southern Ocean is iron-limited, nitrogen and phosphorus to spare, but so little iron that phytoplankton cannot bloom despite having everything else. Whales feed deep and release waste at the surface, and that waste is rich in iron. They are fertilizing the very plants their prey eats. Savoca's team put numbers on both columns of that ledger. Before industrial whaling, Southern Ocean baleen whales recycled around 12,000 tons of iron a year. What remains recycles about 1,200 tons, 1/10. Seen from above, a swarm dense enough that it stains the water the color of rust, drifts like a slow bruise on gray sea. That is the vertical axis. There is a second running sideways between hemispheres. In May 2025, Nature Communications published work led by Joe Roman at the University of Vermont, describing what the team called the Great Whale Conveyor Belt. Baleen whales migrate thousands of miles from cold, nutrient-rich feeding grounds at high latitudes to warm, shallow, nutrient-poor breeding grounds near the tropics, carrying nutrients with them inside their own bodies. Urine, placentas, sloughed skin, carcasses. More than 3,700 tons of nitrogen and over 46,000 tons of biomass moved each year from high latitudes to tropical and subtropical waters. That figure comes from the closely related baleen species with good enough migration data. The study excluded blue, fin, and minke whales precisely because their tracking data was not strong enough. Tropical water is warm, clear, and poor. Mother and calf pairs alone can move over 2,300 tons of nitrogen into breeding grounds a year, which means the act of reproducing, of carrying and feeding a calf is itself a planetary-scale nutrient pump. The warm water where they give birth has little food in it, so through that stretch, a mother lives largely on fat reserves built up in the feeding season. What leaves her body in those warm shallows is what feeds the ecosystem there. Calves nurse for about 6 or 7 months, usually on the way back to the summer feeding grounds. Feel the temperature change across that skin. Near freezing water at one end of the journey, water like a warm bath at the other. The same body linking both every year. A vertical axis from the dark into the light. A horizontal one from the poles toward the equator. That is not an animal eating and traveling. That is a distribution network. And the network has one stage left. Transport keeps matter inside the system. But there is a single act in this animal's life that pulls a large quantity of carbon out of the atmosphere entirely for centuries. A 150-ton body does not vanish. It goes somewhere. NOAA Fisheries put a number on it in 2024. Across its life, a single great whale holds an estimated average of about 33 tons of carbon dioxide. NOAA offers its own comparison. A living oak, among the most efficient carbon-holding trees there is, takes up roughly 12 tons of carbon dioxide across a lifespan that can run to 500 years. One whale holds nearly 3 times that in a life of a few decades. The word for this is sequestration. Carbon pulled out of the atmosphere and held somewhere it will not return from for a long time. For a tree, that place is wood. For this animal, the floor of the ocean. When a great whale dies offshore, the body sinks to the abyssal plain, the flat, permanently cold and lightless floor of the abyss. The event has a name, whale fall. And according to NOAA, the carbon in that body can stay locked down there for hundreds to thousands of years. The descent takes hours, slow and steady, into water holding at about 39 degrees Fahrenheit. NOAA calls a whale fall a sudden, concentrated food source arriving where there is almost nothing to eat. And this is where the story turns, and the turn is short. For almost every species, death is when it stops participating in the system. For this one, death is among its largest contributions to it. Economists at the International Monetary Fund, writing in 2019, estimated a single great whale at roughly $2 million in ecosystem services across its life. Carbon capture, fisheries, tourism, and the world's whales at more than $1 trillion. There is one more system to open, and it is not made of matter at all. A blue whale call is infrasound. Very low frequency, roughly 10 to 39 hertz. Most often, 14 to 20 hertz. That sits below the floor of human hearing, one of the most powerful sounds anything alive makes, and almost nobody has heard it. At 15 hertz, you feel it before you hear it, a pressure in the chest, like a heavy truck passing close. On loudness, a sperm whale click peaks near 230 decibels, re 1 micropascal. But that is a pulse 100 millionths of a second long, used to echolocate. What the blue whale holds is a different quantity, a sustained, low-frequency call. The reason those calls travel is planetary plumbing, the SOFAR channel, short for sound fixing and ranging. At a certain mid-depth, temperature, pressure, and salinity combine into a natural acoustic duct. Sound entering it is bent back and forth between layers instead of escaping, carrying hundreds of miles while losing almost no energy. And NOAA notes that under some conditions, it can be heard across an entire ocean basin. The planet came with a fiber optic cable already installed. The honest range is hundreds of miles. In the right conditions, perhaps 1,000. We found the channel during the Second World War. In spring 1944, Woods Hole scientists Maurice Ewing and J. Lamar Wurzel sailed the research vessel Saluda to test a prediction. Low-frequency sound should travel enormous distances through the deep sea. Off Eleuthera in the Bahamas, a second ship dropped 4-pound charges timed to detonate at depth, out to 900 miles from the Saluda's hydrophone. They heard them. Then came the figure that stopped people. Receivers at Dakar, on the west coast of Africa, caught the same detonations from roughly 2,000 miles away. That was the moment humans found the channel. The other species had been using it far longer. We did not invent the ocean's communication network. We wandered into one already running, and took until the mid-20th century to notice we were inside it. What is the signal saying? In October 2020, Current Biology carried a finding from William Ostreich at Stanford and John Ryan at MBARI. The ratio of daytime singing to nighttime singing, on its own, tells you whether a blue whale is staying to feed or preparing to migrate. Through summer and early autumn, they sing more at night, feeding, staying put. In late autumn, as migration approaches, the ratio flips, and daytime singing takes over. John Ryan described the moment it surfaced. In the place where the day and night lines separated and came back together, sat a signal neither of them had expected. How do you know that is not noise? The audience for this kind of thing deserves the method. The data came from a single fixed hydrophone installed in 2015 about 18 miles off Monterey at a depth of around 3,000 feet, wired into MBARI's Mars-cabled observatory. A fixed listening post only tells you how a region is singing, so the team cross-checked it against tags on individual animals. When a pattern measured across hundreds of miles matched the behavior of specific tagged whales, the signal was confirmed as real. Beginning in 2001, John Hildebrand at the Scripps Institution of Oceanography and Mark McDonald noticed that the pitch of blue whale song was falling steadily across decades. Comparing U.S. Navy recordings from the 1960s, preserved on magnetic tape, against modern ones, the frequency had dropped roughly 30% over 40 years. Play the old tape in a lab and you get analog hiss, then a long, low note. Record the same species this year, and it sits audibly lower. What makes it a genuine mystery rather than a local oddity is that the trend repeats consistently across separate populations, Antarctic, Central Pacific, even though each population sings a different song. The team tested the three obvious causes: ocean acidification, shifts in body size and density after whaling, and rising ocean noise. None fit. And the reason is a lovely detail about method. The frequency decline is very nearly a straight line across 40 years. Acidification, body size, and population density all change on other rhythms. None of them produce a straight line. The hypotheses were not rejected for lack of evidence. They were rejected for being the wrong shape of graph. The leading hypothesis on the table, and the one Hildebrand leans toward, runs like this. After commercial whaling stopped, populations slowly recovered. Density within a given stretch of sea rose, and males no longer needed to sing as loudly or as high to reach a distant female, so they could afford to sing lower. If that is right, it carries a strange implication. The drift in the song may be a trace of recovery, the sound of a population that no longer has to call across as much empty water. But it is not proven. This is a species whose stored carbon we have measured, whose recycled iron we have quantified, whose migration calendar we can read off a microphone. And we do not know why its voice is getting deeper. Ship noise is generated mostly below 500 Hz, the same low band a blue whale call occupies. Inside the SOFAR channel, that noise propagates the same way the call does, losing almost nothing over distance. The consequence is not that the animal finds it unpleasant. The mechanism has a name: acoustic space loss. The volume of ocean within which one individual can still be heard by another shrinks. Two people can still talk in a running factory. They just have to stand much closer. Through the early months of 2020, as global shipping dropped sharply, a study using 5 deep hydrophone stations across the Pacific, Atlantic, and Indian Oceans recorded noise falling by 1 to 3 decibels in the 10 to 100 Hz band at most stations, from early February through the end of June. The clearest signal came from Ascension Island, about 2 decibels on average, reaching 3 decibels in the 40 to 70 Hz band during April and May. It is the only real measurement we have of how quiet the ocean gets when traffic thins. Decibels are logarithmic, so a drop of about 3 decibels means sound intensity cut roughly in half. Researchers estimate that across many regions, an individual whale could be heard twice as far in 2020 as in 2019, without singing any louder. From below, a container ship is a low hum with no beginning and no end, pressing in from every direction. For a few months, it thinned. In Hauraki Gulf in New Zealand, where small boat traffic collapsed during lockdown, dolphins and fish extended their communication range by about 65%. Bottlenose dolphins and big-eye fish, not blue whales. The most recent IUCN assessment, from 2018, puts the global population between 10,000 and 25,000 animals, perhaps 5,000 to 15,000 of them mature, against an estimate for 1926 of at least 140,000 mature individuals. The cause was commercial hunting. 2 legal dates, and they are different things. The IWC protected blue whales specifically from 1966. The industry-wide commercial moratorium is separate, voted 1982, in force from 1986. For years after 1966, most continuing losses came from Soviet fleets working outside the rules, their reported books falsified. The scale surfaced only after the Soviet Union fell, when Russian scientists, led by Alexei Yablokov, published the internal records. Nearly 180,000 whales unreported between 1948 and 1973. South Georgia was hit hardest of all. 42,698 blue whales taken there between 1904 and 1971. Afterward, almost nothing. Dedicated ship surveys from 1998 to 2018 produced exactly one sighting. Then, February 2020. A survey by the Wild Water Whales Project at the British Antarctic Survey logged 58 sightings plus acoustic detections, the highest count since the practice ended there. Picture that deck. Gray swell, wind, and a spout on the horizon that nobody aboard had seen in 20 years of this work. Lead author Susanna Calderon, with Dr. Jennifer Jackson, called it a year with more sightings than the team had dared hope for. Off California, the second case. Cole Monahan and Trevor Branch at the University of Washington, publishing in September 2014, set historical North Pacific losses, about 3,400 animals between 1905 and 1971, against a current population of roughly 2,200 from Mexico to Alaska. Their conclusion? About 97% of pre-whaling level, the first and so far only blue whale population confirmed to have essentially recovered. By head count, the system stands at 1/10 to 1/6 of its old scale, and by capacity, iron recycled, nitrogen moved, carbon sequestered, roughly the same. But unlike an organ cut out, this one is growing back, and in 2 stretches of ocean we have measured how fast. The remaining question is what stands in its way right now. Along the U.S. West Coast, an estimated 80 or more great whales a year, blue, humpback, and fin, are killed by ship collisions. Between 2015 and 2024, 118 strikes were reported, 75 of them in California. Scientists estimate only about 5 to 17% of whale carcasses are ever found, so the true number is almost certainly several times higher. The same gap that hid the birth of the species. Under the U.S. Marine Mammal Protection Act, each population gets a threshold called PBR, potential biological removal, the maximum that can be lost each year to human causes while the population still recovers. For blue whales in U.S. waters, NOAA puts it near 4 animals a year. In the Santa Barbara Channel alone, one estimate found roughly 10.6 struck a year, one channel exceeding the threshold for the whole population. The California coast is at once a seasonal feeding ground and home to the busiest ports in the United States. 2 systems, one planetary and one human, sharing one patch of ocean at the same time of year. From the bridge of a container ship, a 100-foot body just under the surface is nothing you would feel. And in this story's units, each animal lost is not one animal. By the measure from Chapter 8, roughly 33 tons of carbon dioxide that never reaches the bottom. Now, the Valve, a voluntary vessel speed reduction program along the California coast, run as WhaleSafe and Blue Whales Blue Skies, has 3 consecutive seasons of results, each larger than the last. 33 companies and 375,000 nautical miles at 10 knots or less in 2023. And by 2025, 787 transits from 44 carriers, covering more than 481,000 nautical miles at whale-safer speeds, cutting the risk of a fatal strike by up to 50%, with cooperation at 68% in Southern California. Why the ocean and nowhere else? On land, body mass grows with the cube of an animal's dimensions, while the load-bearing cross-section of bone grows only with the square cube law. So land animals hit a ceiling around 100 tons. Past that, the skeleton cannot carry the body. In water, that constraint is lifted. Buoyancy cancels nearly all the apparent weight, so the skeleton is barely holding the body up. Put precisely, it is not that this animal wanted to be enormous. Earth's gravity, combined with the density of seawater, is the only condition on this planet under which a size like that is possible. The tons of iron and nitrogen, the carbon, the miles of transmitted sound, all of it is the product of a particular planetary arrangement, not of one animal. A blue whale skeleton hangs in Hintsa Hall at the Natural History Museum in London. It belonged to an animal stranded at the harbour mouth in Wexford, Ireland in 1891, after being injured by a whaling vessel. The interesting part happened in 2017. The museum lifted that skeleton into the most prominent position in the building, replacing Dippy the dinosaur, and named it Hope, a stated shift from a wonder already extinct to a wonder still living and still keepable. Stand in that stone hall, hear your footsteps come back off the walls, and look up. Two kinds of wonder side by side. One that stopped running long ago, and one running right now, somewhere out there, lifting iron into the sunlit layer and sending a 15 Hz note into an acoustic duct older than our species. We know how much carbon it holds, how much iron it recycles, how far it travels, and in which month. We still do not know why its voice is getting deeper. That is the distance between measuring a system and understanding it. And in the deep sea, that distance is still wide. We have spent a century asking how big it is. That question has an answer, and the answer is close to the least interesting thing about it. The other question, how differently this planet would run without it, is one we are only now assembling enough units to ask. If you have ever seen a whale in open water, I would like to hear about it, where you were, and what you remember about that moment.